Today we are examining polynomials of higher degrees higher than 2. So cubics, quartics, quintics, 6th degree, 7th degree, higher degrees than 2. And we're going to find out, we're observing that polynomials have some basic features. So several basic features that I need you to be aware of. The first of which is continuity. Polynomials are always continuous. That is a term that we use in calculus a lot because it's the basic condition for many things that we do in calculus. And it's true of all polynomials. So a function is continuous if it has no breaks, no holes, or no gaps. Okay, so this, I graphed all these on Desmos. This is a 5th degree polynomial, and you can see we can draw it without lifting up our writing utensil. It's all one piece, no breaks, no holes, no gaps. This is a function, but it is not continuous. It's not continuous because when I draw it, I have to pick up my pencil, my writing utensil. Okay, this has a vertical asymptote, not continuous. The type of discontinuity is an infinite discontinuity. You don't need to know that. Just know it's not continuous. This also is not continuous because it has a hole. It's called a point discontinuity. This is not continuous because this one has a gap, a jump to it. All right. I made this with a piecewise function, two different functions graphed together, a piecewise function to make that. So not continuous, not continuous, not continuous, continuous. All right. There are lots of non-polynomial functions that are also continuous, but all polynomials are continuous. The second feature that polynomials have is that they have no sharp turns. No sharp turns at all. It is nice and smooth, no sharp turns. We call those corners or cusps. Okay, this is a function, and it is continuous, but it has some sharp turns in it. There's a sharp turn right here, and there's a sharp turn right at the origin, and then there's another sharp turn right here. Again, I made this using a piecewise function. This one is continuous, but it has several sharp turns, several corners or cusps. Okay? All right. The next feature of all polynomials is that they have a predictable end behavior. Predictable end behavior. We know what the ends are going to look like for every polynomial. All right, let us consider this function here, and I got some values of it. When x is 0, we're at -5. When x is 1 or -1, we're at -11. 2 or -2, we're at 7. 3 or -3, we're at 157. -4 and 4, 619. And then 5 and -5, we're at 1645. What do you think would happen? We're only at -5. What do you think would happen as x got extraordinarily small? Extraordinarily small, like approaching -infinity. What do you think it would be? It would be huge and positive, true? As x approaches positive infinity, as x gets very large, the function is getting very close to, it's approaching infinity. It's getting extraordinarily large. Okay, so we say as x approaches infinity, f of x approaches infinity. But writing that out is very tedious. So we have a shorthand way to write all that out, and it's called a limit. All right. The way I would read this is the limit as x approaches infinity of f is infinity. So as x approaches infinity, f approaches infinity. That's what this means. And we can say the same thing for x going to negative infinity. As x approaches negative infinity, the function approaches infinity. The function is infinity as x approaches negative infinity. All right, so limit notation. Okay, if you don't like limit notation, you can write all of this out. And that's fine too, because they mean the same thing. But you need to know limit notation because you'll see it. All right, so your choice. Okay, all right. So, that was true of this fourth degree polynomial. That was true of that fourth degree polynomial. Notice that we did have some negative values in here, right? Even though both functions go to positive infinity as x approaches infinity or negative infinity, both functions go to positive infinity. However, not everything is even positive. All right? So this function, this fourth degree polynomial, both sides went to positive infinity. If I examine the limit as x approaches infinity of f of x, and we know by looking at this table it's going to be infinity, but let me put in this function. Instead of putting f of x, I'm just going to put the function. Okay, what if we were given it in this format instead of this format? I don't give you the answer. Okay, what I see here is I am putting a very, very large number in for x, a very, very large number in for x. And as x is getting extraordinarily large, this -5 down here is not going to have any effect whatsoever on this function. So I can ignore it. Okay? Then I'm left with a fourth degree term and a second degree term. As x approaches infinity, as x gets huge, this term will have no effect on it either. Just like the -5, the -5 had no effect. This is negligible. These are both negligible. Okay. Negligible. Okay. Those are both negligible as x goes to infinity. Those are both negligible as x goes to infinity. So I'm actually putting a very, very large number in for this x. Then I'm raising it to an even power. It's still going to be positive, true? This is infinity. Okay? All right. What would happen? What would happen, do you think, if I changed this function and I made it the limit? Let's find out what is happening. What if I just put a negative in front of that x to the fourth, made it -3x to the fourth minus 9x squared minus 5? Well, in fact, let's make both those positive. What the heck? We'll just flip this over the x-axis. Okay. If I have that, well, x is still going to infinity. The 5 is still negligible. The 9x squared is still negligible. Now I'm putting a huge number in for x, raising it to the fourth power, and then multiplying it by a negative. This thing is going to be negative infinity. Let's take a look at some graphs. Let's consider these polynomial functions and their graphs. This function has its highest term, its highest degree term as 3x to the fourth. This is 2x to the sixth. This is x to the eighth. And we see that as x approaches negative infinity from the left, we are definitely up here going to infinity. As x approaches positive infinity, the function is also going to positive infinity. Same thing on this side, or for this function, same thing for this function. So both of those have end behavior they're both infinity. The limit as x approaches negative infinity is infinity. the limit as x approaches positive infinity of this function is infinity as well. Okay, turn off the sound of my phone. Okay, what if there's a negative lead coefficient? These don't matter. None of these matter. The only thing that affects end behavior is the leading term, the highest degree term and its coefficient. What if your highest degree term, oh, this is not correct. I think this was a sixth. It may have been a fourth, but that's a typo. It's probably a six. I don't know what it is. But anyway, what if it's this? That doesn't even look like the right function for this. Anyway, I'll have to fix that. I'll fix that. I actually think that this was w of x is negative x to the sixth plus like 1 or something like that. We'll make that like that. Okay, anyway, the point is the highest degree term is negative x to the sixth. And this time, they're both, the limit as x approaches negative infinity of the function is negative infinity, and the limit as x approaches positive infinity is also infinity. Highest degree term, negative and negative infinity. Highest degree term, negative and negative infinity. So what is your conclusion for this? Well, the conclusion for that is if the degree is even, gosh, I can't write today. If the degree is even and the lead coefficient is positive. If the degree is even and the lead coefficient is positive, then we're dealing with these. Then the limit as x approaches negative infinity of your function is positive infinity, and the limit as x approaches positive infinity of your function is infinity. If the degree is even, and the lead coefficient is negative, then both of those limits, gosh, golly Moses, okay, both of those limits are negative infinity. So it all depends. If the degree is even, then you only have to look at the lead coefficient to get both of those limits. Let's look at some odd degrees, some odd degreed polynomial functions. Okay, so odd degrees, positive lead coefficient. Odd degree, positive lead coefficient. What are the end behaviors? As x approaches negative infinity, the function is going to negative infinity. As x approaches positive infinity, the function is going to positive infinity. Positive lead coefficient, as x approaches positive infinity, the function will always be infinity, regardless of if it's even or odd. If the lead coefficient is positive, as x approaches positive infinity, the function is going to infinity. Okay? If the lead coefficient is negative, then it's backwards. So as x approaches positive infinity, we're going to negative infinity. As x approaches negative infinity, we're going to positive infinity. So odd degree, positive lead coefficient, or negative lead coefficient. Okay, positive lead coefficient, as x approaches negative infinity, we are going to negative infinity. As x approaches positive infinity, we're going to positive infinity. negatively, both of those are switched. So as x approaches negative infinity, the function is going to positive infinity. As x approaches positive infinity, the function is going to negative infinity. Okay, I know I spent a lot of time on that, but it's pretty important stuff. Very important to know how to sketch these just by looking at them. Okay, and I did summarize that in this box over here. Okay, so you can highlight as you see fit. All right, the next thing to talk about are zeros of polynomial functions. Okay, let me look back at this fifth degree polynomial. So this was a fifth degree polynomial. When I did this on Desmo, it's a fifth degree polynomial, and notice that it has 5 zeros. A fifth degree polynomial, every fifth degree polynomial has at most 5 real zeros, at most. Okay, and at most 4 relative extrema, relative mins and maxes. So that's the first thing to know. If f is a degree n polynomial, then f has at most n real zeros. Okay, it has exactly n. I need to fix that on your notes as well. Okay, has at most n real zeros. F has exactly n complex zeros if you consider multiplicity. Okay, so some zeros can be imaginary, some zeros can be repeated. The graph of f has at most n minus 1 relative extrema. Okay, so degree 5 means you have at most 4 relative mins and maxes. Okay, a word about zeros of polynomial functions. Okay, when f is a polynomial function and a is a real number, the following, all of these are equivalent. X equals a is a zero of the function f. X equals a is a solution of the equation f is equal to 0. X minus a is a factor of f. And a0 is an x-intercept of the graph of y equals f of x. Okay, so we use those interchangeably. Another one we use in there is a is a root of f. Okay, root and 0. Okay, let's talk about multiplicity of zeros. So let's consider this function. When I factor that, it factors into x minus 1 to the 4th power. If I set this equal to 0 and find the zeros, we could find there's only one 0. This 4th degree polynomial has only one real 0, but it is repeated. It has a multiplicity of 4. What does the graph of that look like? Well, let's look at it. The graph of that, let me find a spot where there's no glare. You know what, let me start by x squared. Here's x squared. There's the graph of x squared. Okay, now let's graph the graph of x to the 4th. It's similar, but it is not a parabola. It's flatter than a parabola. What do you think the graph of x to the 6th would look like? Even flatter than the x to the 4th. You see it's even flatter. So they get even flatter and they go to infinity faster. Okay? So they're flattered. All right. If the 0, okay, what if, you see I chose 2, 4, and 6 for our exponents there. What if I chose an x cubed? Let me get rid of these. What if we had an x to the 3rd power? We should know what that looks like. It's one of our parent functions, but there it is. So it still has a flat spot, but it doesn't go through, it doesn't bounce and come off. It goes through the x-axis. What do you think x to the 5th would look like then? Even flatter. Same shape, but even flatter at the origin there. Okay, so if the 0 is repeated an even number of times, the curve will not cross the x-axis at that 0. If the 0 is repeated an odd number of times, the curve gets flat, then crosses the x-axis. All right, a word about imaginary zeros. Imaginary zeros, when you have them, they always come in pairs. They always come in pairs. Let's take a look at, and okay, what do they look like on the graph? Do they cross the x-axis? Absolutely not. They do not cross the x-axis. They always come in conjugate pairs. If a plus bi is a 0, then a minus bi is also a 0. So they come in conjugate pairs. They're not x-intercepts. Instead, they can be seen as a little squiggle. Okay, let's take a look back at a couple of these on the previous page. This was a 4th degree polynomial with only 2 zeros, so that means there must be 2 imaginary zeros, 2 complex zeros. So you can see those up here with the squiggle. Okay, you can see that with the squiggle. This is a 6th degree polynomial, only 2, so that means there are 4 complex zeros, 4 imaginary zeros. So again, you can see those up here with these squiggles. Okay, there's one. This is a 7th degree polynomial, only 1 real 0, so there are 6 complex zeros in here. And you cannot identify them by looking at this like you can a 0, but you can tell, I can tell when there are imaginary zeros in a polynomial. Alrighty. Let's look at some examples, finally, huh? All right, let's find an equation in standard form for a polynomial with these zeros, with zeros of -2, 1, and 3. Well, and we want to find an equation in standard form. Okay, so what is the equation? If these are the zeros, if -2 is a 0, then I know I might just call this function f of x just to call it something. I might call, if -2 is the 0, then x plus 2 must be a factor. If 1 is a 0, then x minus 1 must be a factor. If 3 is a 0, then x minus 3 must be a factor. This is an equation, but it's not in standard form. To get it in standard form, we need to get it in decreasing powers of x. So they're making me multiply this out, which I will do. I'm going to come back here and FOIL this piece out. So we'll have x squared minus 3x minus 1x is minus 4x plus 3. And now I'm going to come in and distribute these through. X times x squared is x cubed. X times -4x is -4x squared. X times 3 is 3x. 2 times x squared is 2x squared. 2 times -4x is -8x. 2 times 3 is 6. So my function in standard form will be x cubed minus 2x squared minus 5x plus 6. Let's find the solutions of this equation if this is my function. So they're asking me, in essence, they're asking me to find the zeros of this function. So I'm going to take my f of x and I am going to set it equal to 0 because they told me to. Okay? All right, let's see if we can factor this. I see that there's an x in common, so I'm going to take an x out first. And what's left is a polynomial, a little quadratic that I know how to factor. It factors with 2 sets of parentheses, x minus 3 and x minus 2. All right, so this is factored form to get the zeros. X would be equal to 0 from this piece, X is equal to 3 from that piece, and X is equal to 2 from that piece. So these two go hand in hand. One of them I give you the zeros and you give me the equation. One of them I give you the equation, you give me the zeros. Going backwards. Find an equation in standard form of a quintic, that's a 5th degree, polynomial function with zeros of 0, square root 3, negative square root 3, and 2i. Well, 2i is imaginary, and if 2i is a 0, then I know negative 2i must be a 0 because complex zeros come in conjugate pairs. Imaginary zeros come in conjugate pairs. So if I want the equation, I'll call it f of x again. The factor when we have a 0 of x is just x. Square root of 3 will be x minus square root 3. Negative square root 3, the factor will be x plus square root 3. 2i, that factor will be x minus 2i. Negative 2i, that factor will be x plus 2i. Okay, again I need to get it in standard form, so I'm going to multiply this out. I'm going to leave the x. I like to come and do conjugate pairs first. Absolutely. Makes it way easier. Okay, x times x is x squared. We have a positive square root of 3x, and we have a negative square root of 3x. Those cancel each other out. Then we have a minus 3. Minus 3. X times x is x squared. These two cancel each other out. And then we have a minus 4i squared, which makes it a plus 4. Okay. Now I think I'm still going to leave my x. I'm going to multiply these two together. So x squared times x squared. Here we have a 4x squared and a negative 3x squared. That makes a plus x squared. And then we have a negative 12 minus 12. And now we have x to the 5th plus x cubed minus 12x. That's standard form. Alrighty. The graph of h is given on the right. Which of the following is true? H could be a 6th degree polynomial. Could h be 6th degree? No, it could not, because even degrees always have the same end behavior. Either they're both going to infinity or they're both going to negative infinity. This is one of them is going to negative infinity, one of them is going to positive infinity. So no, that could not be true. H could have a root of multiplicity 3 at x equals negative 2. Over here at x equals negative 2, could that be a triple root? Sure could. It looks like it is. It gets flat and then it goes through. So yeah, it could. Does it have to? No, not necessarily. It could be a multiplicity of 5, I guess, even though I think that it would be way flatter, but it could be. Okay? From the given information, we just don't know. The lead coefficient of h must be positive. The lead coefficient of h must be positive. Well, this is clearly an odd degree polynomial, and as x goes to positive infinity, we are going to positive infinity. Yes, the lead coefficient must be positive. So D is the correct answer here. Alrighty, let's consider this polynomial, p of x. Let's find the zeros of p. To find the zeros of p, we take p and we set it equal to 0. That's how you find the zeros of a function. Okay, for this one, for this factor, we get the 0, x is equal to 2. It's being squared, so that that 0 has a multiplicity of 2. It's a double root, a double 0. From here, we're going to get x is equal to negative 2/3. If we take this and set it equal to 0, get negative 2/3, yeah? And that's just a single root. And from this one, we get negative 2. Okay, as x approaches infinity, what is p doing? As x is approaching infinity, what is p doing? All right, you guys, what is the degree of this? What is the degree of that one? The degree, this would be an x squared, this would be a single x, this would be a single x. The degree is 4. So this is an x to the 4th polynomial, okay? What sign is the lead coefficient? What sign is the lead coefficient? Okay, well, the lead coefficient here would be a 3 because of that 3 right there. And the 1 here and the 1 here. The lead coefficient is positive. So it's a 4th degree polynomial with a positive lead coefficient. Therefore, both of these are going to infinity. Let's use the information that we're given to sketch a very rough sketch of this polynomial. Here are my zeros. So at 2 and negative 2, at 2 and negative 2, I have zeros. At negative 2/3, I also have a 0, so I think I'll put that over here. Negative 2/3, something like that. It's a rough sketch, right? Okay. We have a double 0 at 2. There's double 0 over here at 2. Everything else is single 0. And my end behavior is up at positive infinity, so I'm coming at it from this side. So I'm going to go through this first 0, through this 0, but for this next 0, I'm not going to go through the x-axis because it's a double root. I'm going to come back up. And that's a very, very rough sketch of that polynomial function. Let's do another one. What about this one? Okay, so let's find the zeros. Take your polynomial, set it equal to 0. From the first factor, we get negative 2 as a 0. From the second factor, we get 3 as a 0. The first 0 of negative 2 is a triple, so we'll have to consider that when we're graphing it. And that's it. There are only 2 zeros, but one is a triple 0. What is the end behavior? Okay, what is the degree? The degree is, I have 3 x's from here and a single x from here, so the degree is 4. What is the lead coefficient sign? Well, this has a lead coefficient of 1, this has a lead coefficient of negative 1. When we multiply all that out, we're going to get a negative lead coefficient, a negative 1 lead coefficient. So as x goes to positive infinity, we're going to negative infinity. As x goes to negative infinity, we're still going to negative infinity. So we're ending down at negative infinity on both sides. Negative 2 and 3. Okay, but negative 2 is a triple. So when I come here, I need to get flat, but go through. Flat, but go through. It's a triple 0. And then over here at 3, I have no idea how high it goes. It may go way up high, or it might go pretty low. I don't know. I have no idea. I'm just going to make it smooth and do that. Okay? It looks a little bit linear there. It should be more curvy there, but whatever. Whatever. Okay. And there you go. So we can tell a lot just by looking at the equation. We can tell a bit about what the graph would look like. All right. Let's consider this function. Okay. All right, x to the 5th. All right, if g is 3f of x, explain how the graph of g differs from the graph of f. Well, g is 3x to the 5th. F is just x to the 5th. What's different about that? Well, this is a dilation. Of the graph of f. It's I should have said vertical dilation. Okay, it's going to stretch it out. It's going to make it go to positive infinity and negative infinity faster. So, of the graph of f. It's a vertical dilation. Okay, now we're going to determine, is g even, odd, or neither? Well, g is 3x to the 5th. True. How do you determine if a function is even, odd, or negative? Oh, I'm sorry, even, odd, or neither? You find what is g of negative x. You replace every x with negative x and see what you get. If I put a negative x in place of x, I'm going to get 3 times negative. A negative to the 5th is still negative. So this is negative 3x to the 5th. G is 3x to the 5th. G of negative x is negative 3x to the 5th. So g of negative x is negative g of x. Therefore, g is odd. Excuse me, g is odd. Okay. What if h is f of x plus 2? How does h differ from the graph of f? Well, h is a horizontal translation, yeah? We're moving x, so it's a horizontal translation. Still can't write. H is a horizontal translation 2 units to the left. Yep, 2 units to the left. Okay. Is h even, odd, or neither? Well, same thing. Okay, let's say, what is h here? H is x plus 2 to the 5th power, right? Because there's f. If we put x plus 2 in for x, we get x plus 2 to the 5th power. So what is h of negative x? If I put a negative x in here, is that negative h? No. Is it the same as h? No. So this is not negative h of x or h of x. Therefore, h is neither even nor odd. Okay, last one. Let's sketch the graph of a polynomial function that is of 4th degree, has one zero that has a multiplicity of 2, so it has a double root, and has a negative lead coefficient. Negative lead coefficient and a 0 of multiplicity 2. And here's where you'll do this in class. I'll walk around, see what your graphs look like. Okay? But mine, I might make my 0 right here. It's a negative lead coefficient. I'm going to put my double 0 there. And then anywhere else, I'm going to have my other 0. Might just do that. There we go. That fits the conditions. Yeah? All right. Now let's do another graph, sketch a graph of another polynomial function with the same characteristics as above, except that the leading coefficient is positive. Well, if the lead coefficient is positive, then we're just going to be going in the other direction. So I might have fun with this and just make it a little reflection through the x-axis. So that satisfies those conditions. All right, we did a lot today with polynomial functions of higher degrees.